These are the notes for Unit 3, Day 2, and we're continuing with the chain rule, and we're looking at more advanced problems today. So, essential question is, how do you get the correct derivative of a composite function when using the definition of the chain rule? So we know from yesterday, we discovered that the chain rule is differentiating, the chain rule is used for differentiating a composite function. So here's our composite function, f of g of x. And the chain rule is basically saying take the outside derivative and with respect to differentiate with respect to f, or differentiate f to get f prime, but leave the inside by itself, and then multiply it by the inside derivative. And this is the Leibniz notation, which is a little clunky, but it's kind of nice because it deals with fractions, you know, and we can see some canceling going on here. So the Leibniz notation is saying we have a function y, kind of like y here, and the inside function is u. And so we take the derivative of y with respect to u times the derivative of u with respect to x. I think the prime notation is a little cleaner. And so the prime notation, the derivative here, we're just going to differentiate this. And that is y prime is differentiating f and then leaving, again, the inside unchanged, and then multiplying that by the derivative of the inside. So so when we're talking about outside and inside, we know that f is on the outside and g is on the inside. And so this, like I said a few seconds ago, dy du is that outside derivative, du dx is that inside derivative. So it's kind of rewriting it as y equals f of function u, and then the function u is that g of x, if we want to kind of connect these two notations. So I said this is a little clunky. And then, and then this prime notation is a little cleaner. And so this prime notation, I think, is more easy to work with, and that's kind of what we're going to focus on. So a lot of times they give you problems that are graphical. And so it says use a chain rule to differentiate r of x. And so they define r of x as f of g of x. So again, we're sticking function g into function f. So in other words, all of g's, here's function g is going into function f. And so to work with this symbolically, we really need to adhere to this definition. We're going to take the derivative of function f at location g of x and multiply it by the derivative of function g. Now, if I say derivative, you think fill in the blank, right? You think slope. So we're going to be dealing with the slopes of these values in order to find the derivative of the composite. Okay, so let's break this down. We want to find r prime of 4, which means we want to find, here's where x is equal to 4. And so the first thing we're going to do is we're going to work with the inside function, g of x. Well, what is g of 4? So here is function g. G of 4 is 5. Okay, so when we're looking at the derivative, then we're really saying f prime, we're using the definition of the derivative here to define symbolically, okay, the r prime of 4. So r prime of 4 is the f prime of g of 4 times g prime of 4, right? If we're looking at this, I'm just sticking the 4s in here and the 4 in here, because that's where it's asking me to evaluate. Well, f prime of g of 4, remember g of 4 is the y value on function g, that's just 5. So really, this is f prime of 5. We can take the g of 4 out and put 5 in because we know what the y value for g of 4 is. So this is really f prime of 5. Remember, I say derivative, you think slope here because you're getting things graphically. F prime of 5 times g prime of 4. So I need the slope here times the slope here. So what is the slope here? Well, let's see here. This is a convenient point. This is a convenient point. Looks like we're going up 1, 2, 3, 4, 5, and we're going right 1, 2, 3, 4. So 5 over 4 for f prime of 5. G prime of 4 looks like we're going up 1, right 2. So slope of a half for G prime of 4. Multiply those together, we get a slope of 5/8. So that's the derivative of r prime of 4. Now we can actually build f of g of x. We can build function r. So I'm going to kind of do that. And if you want to write this down in your notes, you can. And but you don't have to. Adhering to the definition here is really what we want you to be able to do because it's a lot quicker. But let's do this. Okay, we're going to build r of x. So r of 0 is f of g of 0. So let's think about that. G of 0 is 4. So r of 0 is f of 4. So f of 4 is whatever that value is, right? That looks to be, I'm not sure what that is. I just slid that right over to the r of 0 location. Okay, now let's look at r of 1. R of 1 is f of g of 1. Well, g of 1 is 4. So I need f of 4. So f of 4 again is this value. I'm not sure what it is, but I'm just going to slide it over to r of 1. I just know I need that y value. R of 2 is f of g of 2. G of 2 is still 4. So I'm going to go to f of 4. I'm going to grab that value. That's my r of 2. Okay, so r of 3, this is where it gets interesting because it finally starts to change. R of 3 is f of g of 3. Well, g of 3 is this value here. And we know that's 4.5, right? Because we're going to go up 1, right 2. So this is 4.5. So here is 4.5. F of 4.5 is that y value. That's my r of 3. Notice that I'm not really calculating the values. I'm just sliding them to where they need to go. Okay, r of 4 is f of g of 4. Well, g of 4 is 5. So we need f of 5, and f of 5 is this y value here. Again, I don't know what it is, but I know that should be r of 4. So I'm going to slide it over to 4. Where are we? R of 5 is f of g of 5. So g of 5 looks like it's 5.5. So I'm going to take f of 5.5, and that's my r of 5. So I'm going to slide that over to where the x value of 5. And r of 6 is f of g of 6. Well, we know g of 6 is 6. And so f of 6 also happens to be 6. So there's my final point, r of 6. So there's function r. And I want to know r prime of 4, right? Well, r prime of 4 is just the slope right here. Well, what is the slope right here? Well, it's the slope of this line. So let's calculate that. We're going to go up a half, 1.5, 2.5. We're going to go up 2.5. We're going to go right 1, 2, 3, 4. Well, 2.5 over the 4 is the same as 5 over 8. So you can see we can build r and graphically, and then we can just calculate the slope of r at 4 if we wanted to, but that takes a lot longer than just working with the definition using the chain rule. Okay. The other thing that they like to do is they like to give you tables, and again, that's to make you work symbolically. So they're asking you to evaluate this function. This is a following table lists the values of functions f and h, and of their derivatives f prime and h prime for x equals 0 and x equals 2. So they're giving you 2 rows, right? We know we need 2 rows because the numbers in the blue bracket and the number in the green bracket end up being 2 different numbers. And it says evaluate the derivative of f of h of x at x equals 0. So the first thing I'm going to do is I'm going to take this notation and I'm going to plug in my 0. So I want the derivative of f of h of 0. Well, using the definition, we know that's the derivative of f at h of 0 times the derivative of h of 0. So the first thing I want to know is what is h of 0? What is this value? Well, I go up to my table. This is not the derivative, this is just a function value. So h of 0 is 2. So I know that by definition, I want the derivative of h of 0 times the derivative of h of 0. So the derivative of f at h of 0 is the derivative of f at 2, because we know h of 0 is 2 from the table. And then we need the derivative of h at 0. So now we can pick these two derivative values. So we're looking at the derivative columns now. So f, the derivative of f at 2, go to where x equals 2, come over to the f derivative, that's 3. And then the h derivative at 0 is negative 3. So this derivative is negative 9. Okay, so here's kind of as advanced as we really can get. This is a function. So if we think about the notes we've taken so far, we've done a graphical chain rule, we've done a tabular chain rule, and now we're doing an algebraic or a function-based analytic chain rule. Okay, but we're still adhering to that definition of the chain rule, that symbolic definition. Okay, so what do we have to take the derivative of? What are the nested functions here? Well, I see a natural log, and I see an exponential, and I see a power rule, like this x is really x to the first power. So I got three things going on here. Okay, so let's build this function. We have the function h of x, which is f of g of x, and we want to know what the derivative of h prime is. Okay, so let's build f of g of x. So that means I'm going to take the function f, which is a natural log of x, and everywhere I see an x, I'm going to put in g of x. So we know g of x is e to the 2x plus x. I'm going to write that like this, because we know that power location is another grouping location. So we have a chain rule already in g of x, because we have e to the 2x. Okay, so h of x then is going to be taking this and sticking it into the natural log. So it's going to look like this. Okay, so we have a natural log with an exponential with a power rule. And then we get a power rule hanging out here too. So h prime of x then is taking the derivative of the natural log, right? That's this notation. F is on the outside. It's taking the derivative of the natural log at e to the 2x plus x. That's the g of x. Times the derivative of g of x. Okay, so let's start differentiating our pieces. The function f, the outside function, is a natural log. We know its derivative looks like 1 over x, but really it's going to be 1 over whatever we see, which is g of x on the inside. So that's g of x, and the derivative of g of x is going to be differentiating this. So that's going to be e to the 2x times 2. There's your chain rule because of this nested function. And then the derivative of x is just 1. So putting this together then, f prime of g of x is going to be 1 over everything on the inside, right? We just leave the stuff in the brackets alone when we're doing the outside functions. And then times the inside derivative, which is that 2e to the 2x. So rearranging this, we would get h prime of x is equal to 2e to the 2x plus 1 over e to the 2x plus x. And that's as simple as it gets. We can't cancel anything here because we don't have we don't have it expressed as factors. So we just leave the derivative in that form. Okay, so when we get back into class, then we'll go over the takeaways and we'll work on some more advanced more advanced chain rule problems.